So suppose we flip a coin 4 times, the most probable outcome is going to be 2 and 2. We have 4 independent tosses, produces 16 possible different outcomes. And this is me saying that as soon as you get to 5, 6, that it takes so long for you to write them out yourself. It isn't worth doing, okay? But we have our all heads, okay, right? 6 of these have 2 heads and 2 tails, right? Heads, heads, tails, tails, heads, tails, heads, tails, tails, heads, heads, tails, right? So these are all the different ways that you can get 2 and 2, okay? And in all of these situations, I don't care what order they turn up in ever for us in this class. Okay? So there's 6 ways to get 2 and 2. The probability is 6 divided by the total 16 outcomes that could happen. So the probability of getting 2 heads and 2 tails in some combination is 38% or 0.38 is our probability. Okay. Number of ways it can happen, 6. Total number of possible things that can happen when I flip a coin 4 times, 16. And so multiplicity is the top number, this 6, 4, 1. Okay. 2 heads and 2 tails has the highest multiplicity. It also has the highest entropy. It's the most likely outcome, the most probable outcome. It also looks the most disordered. Okay. So these are, again, just our definitions of the macro state and the micro state. The most probable macro state for a system will be the one that is achievable by the most different microstates. Okay. Another way to say this would be the second law of thermo, the principle of maximum entropy, says that a system will always tend towards whichever state maximizes the number of microstates. Whatever maximizes multiplicity is what we're headed towards. Okay. So again, in this case, from the macro scale, the temperature, the pressure, the volume, the number of molecules of solvent and dye I have is exactly the same here and here. None of those things are different from a macro scale. But this is still going to happen because the number of ways they could distribute throughout the whole glass, there's way more ways for that to happen than for this to happen. Okay? So Boltzmann, again, he had a statistical view of entropy. He's the one that said the macro state with the highest multiplicity is the one that's going to be most probable, okay? And sort of defined entropy this way, whatever has the highest multiplicity. Okay. So multiplicity of 4 events, pretty easy, but if you want to use, say, 40, 100, 1,000, it gets increasingly difficult. So we're going to use something called binomial coefficient, and this is the way it will be in your book, okay? Given to you on your equation sheet. Okay. I have m total observations, so in this case, m is my coin flips, okay? 40 coin flips. And n events, this is event of interest, okay? Head or tails. You have to specify which one you want, okay? So how many tosses are there? How many times did heads come up? What does my little exclamation point there mean? Factorial. How do you take a factorial? What is 4 factorial?
4 times 3 is 8.
Perfect. 4 factorial is 4 times 3 times 2 times 1. What's 0 factorial? 1. Let's take the product, okay, across I from n down to 1. And 0 factorial is equal to 1. So when you're asked for how many different ways could I get some things, we already said, we showed on the last slide that the multiplicity of our 2 heads and 2 tails was there were 6 different ways to do it. But we can use the multiplicity equation to convince ourselves of that. So on the top is the number of different tosses I'm doing, m factorial. So how many different tosses was I doing on the top? 4. Okay. For 2 and 2, n is my number of outcomes of interest for heads, that's 2 factorial. The other outcome was tails. Okay, so this is 4 times 3 times 2 times 1. This is 2 times 1 times 2 times 1. This cancels out, and I have 12 divided by 2 is equal to 6 different ways. Okay. I was gonna maybe ask you if you thought the binary outcome of a coin flip was a useful analogy, but it is a very useful analogy, okay? Things like bound or unbound are a two-state situation, right? So binomial means there's only 2 options, okay? They don't have to be equal probability. It doesn't have to be 50-50 chance, but it means there's only 2, right? Heads or tails. In this case, it's I'm either bound or I'm not bound, right? The drug is on or off. For a protein, it's either folded or it's unfolded. It's one or the other, okay? If anyone's familiar with NMR, okay, or an MRI, you have all of you basically use water, but you're in a magnetic field, and you're gonna align all of your spins with the field, okay? And then you knock them out of place, and then you give them time to come back, right? So orientation of any of these protons with the magnetic field, parallel with the field, would be sort of one state, anti-parallel would be the other state, 2 states. Okay. And like I said, we're kind of building to energy distributions on Thursday, but a way to think about this is, again, most of our biological systems can be treated like a binomial case, just on or off, yes or no, bound, unbound, fold, unfold.